Hey everyone, let's have a crack at another challenge that we posted earlier. Today, I wanted to sit down and just really dig into something that I think gets a bad rap in system design interviews. We're talking about TinyURL. And look, I know, you've seen this question 100 times. People roll their eyes. Oh, it's just a hash function. Oh, just throw a load balancer at it. And I get it, because usually the canned answer is enough to pass the interview and everyone moves on. But here's the thing. The moment you put the word trillion in the constraints, everything changes. Like, genuinely, the rules of physics for the system just shift under your feet. So here's our setup. We need a service that takes a long, ugly URL, you know the ones, 500 characters, UTM parameters, tracking garbage at the end, and we squish it down into a 7-character alias. 3 constraints. 1, 7 characters max. 2, unique, no collisions, absolutely 0. And 3, 1 trillion URLs over the entire lifetime of the system. Now, if you're coming from a background of building normal scale apps, you might say, okay, I'll just MD5 the URL, grab the first 7 characters, and save it to Postgres. Problem solved. Are we getting lunch now? No, not quite. Let's do some math. The classic back-of-the-envelope stuff. If you take a 128-bit MD5 hash and you throw away all but 7 characters, you have discarded about 90% of the information that made that hash unique in the first place. You've essentially crumpled up the uniqueness guarantee and tossed it in the bin. And the birthday paradox, you might remember this from probability class, says that collisions start showing up way earlier than your intuition tells you. With a trillion records and a truncated hash, collisions aren't a risk, they are a mathematical certainty. They will happen. And a collision here isn't just a bug, it's a disaster. Someone clicks a link to their wedding photos and they land on a spam pharmacy because 2 URLs happened to hash to the same 7 characters.
So what do people usually say to fix this? They say, okay, fine. If there's a collision, I'll just salt the URL and rehash it until I find something unique. And then you end up with what I call the check then insert pattern. You hash, you check the database, it says exists, you hash again, you check again. At the scale of 1 trillion records, your database index is potentially several terabytes. Every single collision check is a disk seek into that index. If you have heavy write traffic, you're spending most of your compute budget just verifying that you haven't used a string before. That's O of n in the worst case. That just doesn't work. What we actually want is to flip the mental model entirely. We want to stop searching for uniqueness and start generating uniqueness. That is a subtle shift, but it is a really important one. It's almost like, okay, bear with me here. It's like the difference between searching a dictionary every time you need a word versus just knowing the word already because you built the dictionary yourself. So how do we generate uniqueness? The simplest way to guarantee a number has never been used before is a counter. Every time someone shortens a URL, counter +1. Counter number 1 is the first URL, counter number 1 trillion is the trillionth. We mathematically cannot produce the same number twice. But we can't hand the user a giant integer. The constraint says 7 characters. So our problem becomes, how do we map a large integer, the counter value, to a 7-character string? And this is where base 62 encoding comes in. Think about how we count in everyday life. Base 10, 10 fingers, 10 digits. Computers use base 2, binary. Programmers use base 16, hex, all the time. We have 62 characters available to us. Uppercase A through Z, lowercase a through Z, digits 0 through 9. So we use base 62. The math works exactly like long division. Say our counter is at 125. 125 divided by 62 is 2 with a remainder of 1. Remainder 1 maps to the character at index 1 in our alphabet. Let's say that's B if A is index 0. The quotient 2 maps to C, so counter 125 becomes the string CB. This is called a bijective mapping. Every single integer from 1 to 3.5 trillion maps to exactly one unique 7-character string, and you can decode it back, perfectly reversible. And here's what's beautiful about this. It's stateless. I do not need to go to the database and ask, hey, has CB been used before? I already know it was used when the counter hit 125. No lookup needed. Writes become essentially O of 1. Append the new mapping, done. But there's always a but in distributed systems, right? If you have a single counter in a database, some row that you update counter set value equals value plus 1 for every request, and you're getting 50,000 requests per second, you've just created the world's most catastrophic lock contention problem. 50,000 threads fighting for one row. Your system grinds to a halt. It's like trying to have 50,000 people share one pen to sign a document at the same time. So we need to distribute the counter. We need 100 servers, each generating unique IDs without having to phone home to a central authority for every single request. Enter range management. We use a coordination service. Apache ZooKeeper is the classic choice here. ZooKeeper is a distributed, highly available source of truth. It's really good at keeping track of small pieces of metadata, and it's great at handing out work to distributed nodes. Here's how it works. Instead of handing out IDs one by one, ZooKeeper hands out ranges. Server A comes online. It says, hey, ZooKeeper, I need some IDs. ZooKeeper says, take the range from 1 to 1 million. ZooKeeper updates its internal record. Next available range starts at 1,000,001. Server B comes online, gets the range from 1,000,001 to 2 million. Now look at what we've actually achieved here. Server A can handle 1 million shortened URL requests entirely in its own memory. Just increment a local integer. No network calls, no locks, no database checks. Incredibly fast. When Server A is approaching the end of its range, it goes back to ZooKeeper and requests a new one. We've reduced coordination overhead by a factor of 1 million. And if Server A crashes mid-range, we lose maybe 500,000 unused IDs. Does that matter? No. Remember the physics. Our namespace holds 3.5 trillion. We only need 1 trillion. We have 2.5 trillion in reserve. Losing a few 100,000 to a crashed server is honestly a rounding error. Okay, so our ID generation layer is solid. ZooKeeper, local counters, base 62 encoding, we're mathematically guaranteed to never produce a duplicate. But now we have to store the thing. 1 trillion records, each mapping a 7-character string to a long URL. If a long URL averages 100 bytes, that's 100 terabytes of raw data. Add in indexes, timestamps, user IDs, metadata, you're realistically looking at 500 terabytes to a petabyte. You cannot put a petabyte in a single Postgres instance. Even if you could, the B-tree index for 1 trillion rows would be enormous, potentially 12 or 15 levels deep. Every lookup is a cascade of disk seeks. We have to shard, split the data across, say, 100 database nodes. Each node handles 5 terabytes, much more workable. The question is, how do you decide which node holds which URL? Since the most common operation is a redirect, someone clicks a link and we need to find the long URL immediately, we shard based on the short URL. Hash the 7-character string, mod by 100, and that tells you which node to query. This is consistent hashing, O of 1 routing, no central directory. And for the actual database, we don't need ACID transactions. We're not doing joins, we're not doing multi-row updates, we're doing a pure key-value lookup, short string in, long URL out. That's exactly the workload that Cassandra or DynamoDB are designed for. They use LSM-trees, log-structured merge trees, instead of B-trees, which means they handle write-heavy workloads much better. They also handle their own sharding and replication, which simplifies our operations layers significantly. Now, the read path. This is where things get really interesting. You know the Pareto principle, the 80-20 rule? In a URL shortener, it's more like a 99-to-1 rule. 99% of clicks hit 1% of the links. A celebrity tweets something, that one link gets millions of hits in an hour. My mom's link from 3 years ago, probably never getting clicked again. Treating both of those the same is wasteful. So distributed cache, Redis or memcached. Request comes in, check Redis first, cache hit, return the redirect in under a millisecond. Cache miss, go to Cassandra, get the URL, save it to Redis for the next person, return the redirect. How much RAM do we actually need? Well, if we assume 100 million active links per day at 100 bytes each, that's 10 gigabytes, which is nothing. You can fit that on a single cheap server. Even being very conservative and caching 1 billion links, that's 100 gigabytes of RAM. A small Redis cluster handles that easily.
Now, and this is the detail most people completely miss in these interviews, security. Remember our counter? Counter 100 maps to CB. Counter 101 maps to CC. Counter 102 maps to CD. Look at that pattern. If you can see your own short link, you can guess the link that was created right before yours and right after yours. You could write a simple script to crawl the entire namespace. You could discover private links. You could scrape business intelligence, like exactly how many URLs per day the service is generating, which is genuinely sensitive competitive data. We want our IDs to look completely random, even though underneath they're sequential. How? We use a Feistel cipher. This is a technique from cryptography. It's the same structure underlying DES and a bunch of other classic block ciphers. The idea is you take your integer counter value and you run it through a mathematical process that scrambles the bits in a reversible way. Every input maps to a unique output, and you can always reverse it to get back to the original. But to anyone on the outside, the outputs look like random noise. So counter 100 might come out as 8,231,942,001. You convert that to base 62, and you get something like X9K2PQ. Counter 101 might produce something completely different, no pattern visible at all. But internally, still just a counter. No collisions introduced, no database checks added. The uniqueness guarantees are completely intact. We've just added a layer of obfuscation at the generation step. This is the kind of move I love in systems design. You solve a product and security requirement, preventing ID enumeration, using a mathematical primitive, rather than adding architectural complexity. Okay, last piece. What happens when a data center burns down? We're global. Users in New York, users in Tokyo. If the Tokyo user has to wait for a round trip to Virginia for a redirect, that's 300 milliseconds. Bad UX. For reads, we put redirects at the edge with a CDN, Cloudflare or Akamai. User in Tokyo gets served from a Tokyo edge node. Latency, 10 milliseconds. For writes, someone creates a link in New York, we write to the New York Cassandra cluster, and Cassandra asynchronously replicates to Tokyo. This brings up the CAP theorem, consistency, availability, partition tolerance. We can only guarantee 2 of the 3 during a network partition. For a URL shortener, do we really need strong consistency? If I create a link and my friend in Tokyo clicks it 100 milliseconds later and it fails because the replication hasn't quite finished, is that a catastrophe? No. They refresh, it works. Not a big deal. So we choose eventual consistency, high availability and low latency, with a small window where a brand new link might not resolve in a distant region yet. The one thing we absolutely cannot compromise on is uniqueness, and that's the beauty of the range manager approach. Even if New York and Tokyo are completely isolated from each other, as long as they were assigned non-overlapping ranges before the split, they continue generating unique URLs independently, no risk of overlap. They are mathematically isolated from each other. Let me take a step back and actually trace what we built here. We didn't approach this as a URL shortening coding task. We approached it as a namespace management problem. 1. We determined the size of the namespace. 62 to the 7th is 3.5 trillion, which is enough. 2. We reduced uniqueness to a sequential counter. 3. We reduced distributed coordination to range allocation via ZooKeeper. 4. We reduced petabyte storage to sharded key value pairs in Cassandra. 5. We reduced read latency to cache the hot tail with Redis. 6. We solved security with a Feistel cipher. That's the reductionist mindset. At this scale, you cannot brute force your way through problems with more code. You have to find the right abstraction that makes the problem small again. If you go into an interview and you say, "I'll use a hash and hope for the best," you're thinking like a coder, which is fine. But if you talk about the physics of the ID space, if you talk about why LSM-trees beat B-trees for this write profile, if you explain the birthday paradox and what it actually means for truncated hashes, you're showing that you understand how the machine works underneath. That's what I mean when I say understanding why a system fails is more important than knowing how to build it. Anyway, that's TinyURL at a trillion scale. Simple-looking problem, masterclass in distributed systems on the inside. I'll link the ZooKeeper coordination docs and some Feistel cipher implementations in the description. Definitely worth reading if you want to see the actual math working in code. Happy coding, everyone!